Hey everyone, I am Miss Hu, your physics teacher. In this video, we're going to go through the concept of light refraction, where we will cover what is light refraction, what causes light refraction, and calculating refractive index. This video is for those who are taking SPM physics. If you are taking IGCSE physics, please watch my video on light refraction designed for IGCSE students. This is because students who are taking SPM physics will have to learn an extra equation compared to those who are taking IGCSE physics. Now, if you're taking IGCSE physics and you're thinking, oh, there's no harm learning something extra, well, there isn't, but you might panic when you see the extra equation because you would not have learned it in class, you would not have learned how to apply it, and you'd have no practice questions involving it. So let's not give you unnecessary panic. Just head over and watch the light refraction video for IGCSE students instead. So this one is designed for SPM students. This video is designed more of an introduction to light refraction and also can be used as a revision piece, an overview of this particular concept. We will not be going through any worked examples or calculations in this video. Those will be covered in another video. So first things first, what is light refraction? By now, you should know what light refraction is, or at least how it appears in real life. For example, if you place a pencil in a cup of water, you will find that the pencil appears to be bent. And of course, by now you should know, oh, that's because of light refraction. But how do we learn this in theory? So normally, when we want to study light refraction, we will use the example of a glass block placed in air, and we will observe how the light ray travels between air and glass. So let's say we shine a single ray of light from air into the glass. So this yellow arrow here represents that single ray of light. And the arrow, of course, indicates its direction. Now, when the light travels from air into the glass block, we'll find that the light ray changes direction. And then when it travels from glass back out into air, it changes direction once again. So light refraction is the phenomenon where the light ray changes direction as it travels through different mediums due to its change in speed. You must, of course, also be aware of what causes the change in speed of light within these different mediums. And that's because of the different optical densities of the different mediums. Now, some of you may have learned that its density. What is its optical density? Some of you may never have heard of it before. So let's take a pause first. My question to you is, how does density affect light? So see, density is a calculated value where we take the value of the mass divided by volume. So density is the mass per unit volume. One of the first learned and understood density is by comparing density of materials against water. So you place a different objects in water and see whether it floats or it sinks. And if it's lower density, it floats. And if it's higher density, it sinks. So think about all that floating and how heavy it is in water and all that. And think about how that affects the speed of light. The answer, it doesn't. You see, density is more of a comparison of how much mass, how much matter there is in every unit of that volume. But when we talk about speed of light, it's about how fast that light ray can travel through that particular medium. And of course, light can only travel through transparent or translucent mediums. If the object, if the material is opaque, then light cannot travel. So not all objects allow light to travel through it. So all objects have density, but not all objects have optical densities. So that's an important thing to consider. Therefore, density has no effect on the speed of light. So what affects the speed of light is actually something called optical density, which is the measure of how much light has been reduced in that medium. You can think of it as, because density is like how much material there is within that small volume of an object. So optical density could then refer to the amount of the atoms or the particles in that transparent or translucent medium within that small area. So of course, the more particles there are, then the higher the optical density. And then you think, oh, if there's more material packed in that small area, would it be easier or harder for the light to travel through? Well, obviously, if there's more material, it's harder for light to travel through, right? So that slows the light down. That's why the greater the optical density, the slower the speed of light. So a more correct way from this point forth to understand how the speed of light in a medium is affected is that it's not affected by density, but by the medium's optical density. Next, let's look at the calculation of the refractive index of the medium. Now, before we get into that, just to point out to you very quickly, because air has a lower optical density, light will travel faster, whereas glass has a higher optical density, so light will travel slower in glass. So when light travels from air to glass, you can see how the light ray appears to refract towards the normal. So the normal line is a line that is perpendicular to the boundary. And then when light travels from glass into air, because it's moving from slower to faster, it now refracts away from normal. So again, when light travels from a from faster to slower, that means from a lower to high optical density, it refracts towards normal. Whereas when light travels from slower to faster, that means from a higher optical density to low optical density, it refracts away from normal. So that's also an important terminology that you need to learn to use. You need to know how to describe that kind of refraction. So let's learn to calculate the refractive index. So refractive index is something like optical density, but they're not exactly the same. They are related, but refractive index is more of a physics way of calculating how much light has refracted, if you will. So if you remember that in physics, we like to measure everything, right? So it's not enough that we know, oh, light refracts, when traveling through different mediums. Not enough for us to know that, oh, refracts towards and away from normal. We also need to know by how much. So by knowing the exact value, this enables us to predict more accurately how light would refract in different mediums at different angles. So refractive index is actually the ratio of the behavior of light in air and the different medium in terms of refraction. There are a few formula that we can use to calculate refractive index. So the first one obviously relates the speed, because we know that light travels at different speeds in the different mediums. So when we calculate the refractive index, it's always a refractive index of the medium. That means if we have a glass block, we're calculating the refractive index of glass. If we want to observe how the light bends in water and we want to calculate the refractive index, it's the refractive index of water. At this stage, you will not be counting refractive index of air, because the refractive index actually is a comparison of the refracted light ray in that medium against the refracted light ray of the light in a medium against how it travels in air. So the refractive index is comparing the medium against air. So that's why we're not calculating the refractive index of air at this point. If you are wondering, can we compare the refractive index of one medium to another, like from glass to water, or comparing, water to oil, for example? It is possible, but that's not something we learn at IGCSE level. That's something you will learn at higher levels. So for now, at IGCSE level, we just focus on comparing the medium against air. So that's why the formula here, as you can see, is the speed of light in vacuum or air divided by the speed of light in medium. Now, why is it vacuum or air? Because at this stage, we take the value of the speed of light in vacuum and air to be the same. Are they different? Actually, yes. But for now, we assume that difference to be negligible. So at IGCSE level, we take the speed of light in vacuum and air to be the same, which is 3 times 10 power of 8 meters per second. Another way to calculate it is by comparing the angles. But first of all, we need to know a bit more about the terminology used. So again, let's look at the names of the rays. So the light ray that's traveling from the source is known as the incident ray. When the light ray refracts in a medium, that ray is known as the refracted ray. And the light ray that comes out of the glass is known as the emergent ray. When we want to measure the angles, it is always measured from the normal line. The normal line is a line that is perpendicular to the boundary. So as you can see, I've got the gray colored lines here that are dotted, and these gray dotted lines are perpendicular to the boundaries at the point where the light is changing the mediums. So for example, on the top here, when the light is traveling from air to glass, okay, we've got the normal line there. The angles are measured from the light ray to the normal line. So it's always measured between the light rays and the normal line. So on the top here, you can see I've labeled the angle as I in air, and I've labeled the angle in glass as R. So that's how we measure the angles. Now, because in air, that ray is the incident ray because it's coming from the source, that angle is known as the angle of incidence, or also known as the incident angle. The light ray that is traveling in the glass block is known as the refracted ray. So the angle between the refracted ray and the normal line, which I've labeled here as R, is known as the angle of refraction or refracted angle. So that means that you can call the angle either way. Angle of incidence and incident angle, same thing. Angle of refraction or refracted angle, same thing. So not only is the ratio of the speed of light equal, we'll find that the angles also have a ratio, but the angle is not just I against R. So the people, the researchers, the physicists who have done all their research on light, refraction, and all that have found that the ratio is actually based on the values of the sine of the angle. So another way to calculate the refractive index is to take sine I divided by sine R. Now, before we move on, let's learn about Snell's law. Snell's law is the law from which the refractive index equation was derived. Snell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for the pair of the given media. So when the experiment was conducted back then, they found that the angles of I to R are not constant. What is constant is the sine of the angles, and that's where Snell's law was derived. Now the formula for Snell's law is n1 sine theta 1 equals n2 sine theta 2, where this equation can be used for any two given media. For example, it can be calculated for the refraction between water to air, or water to glass, diamond to water, oil to water, plastic to glass, and so on and so forth. So that's why you find that in the formula, we've got 1 and 2, where 1 represents the first medium and number 2 represents the second medium. So N1, which is incident index in this case, is actually the refractive index for the first medium, while N2 is the refractive index, which in this case means the refractive index for the second medium. Theta 1 is the incident angle, while theta 2 is the refracted angle. This means that theta 1 and theta 2 are the angles measured in mediums 1 and 2 respectively. Now for SPM and IGCSE, you don't need to use this formula. This formula is more for A levels. In SPM and IGCSE, you only learn about the refractive index of the medium compared to air. So at A levels, you have to learn about two different media. That's why you have to use this formula. For SPM and IGCSE, this has been simplified to n equals sine I over sine R. This formula is actually derived from this. No, you do not need to know how to derive it. So all you need to do is just know how to use this formula. So for the equation list, I will write down this formula. A little bit about sine I and sine R formula first before we move on. So this is of course comparing the angles when light is traveling from air to glass. But what if we were given angles in the situation where light is traveling from glass to air? Now, based on the name, I know I've written here incident ray, refracted ray, and emergent ray. But let's say if we focus only at the bottom part, where the light is traveling from glass into air, if you just focus on that section, that light ray moving from glass to air becomes the incident ray, and the one moving out into air is known as the refracted ray. So hence, the angles are I and R respectively as well, where I is in the glass block and R is in the air. But the problem is, if you take sine I over sine R based on this, it will not be the same as the one on top, right? Because you can see that overall, the angle of air should always be bigger than the angle in glass. So then it's like, okay, how do we apply this then? If you're wondering, because at the bottom here, at the bottom part where light is traveling from glass to air, the value of I and R are opposite to the values of I and R, which is on the top. Okay, if you don't know what I'm talking about, it's like basically you can't just take sine I over sine R blindly because you've got a whole bunch of different possibilities of I and R in this case. Now, the calculation of refractive index is always based against the comparison of the light traveling in air. So we always take it as light traveling from air into the glass. So even if it was flipped, where light travels from glass to air, although in, in terms of the names, it's still I in glass and R in air, but when you apply the values in the calculation, I should be the angle in air while R is the angle in the medium. Because you must remember that the comparison of the angles here, the refractive index calculations here, are always based against how light travels in air. So we take I, no matter whether it's I in, in this case it's in the glass or something, doesn't matter. Okay, that's the name. But when you do the calculation, however it goes, I must be the angle in air and R must be the angle in medium, even if light was traveling from glass into air. And there's one more formula, which is n equals 1 over sine C, where C is the critical angle. However, I'm not going to go through the critical angle in this video because this is actually under the subtopic of total internal reflection, and that is a whole other concept which will take another maybe 20 minutes to explain. So instead of overloading you, sorry, let me say that again. Instead of overloading you with too much information right now, let's take that into another video where you can find out more about total internal reflection in all its glory. Now, in addition to these three formula, you also need to know of one more formula, but we need to change the diagram to have a better understanding of how to get the values for that equation. Now, this diagram is showing how a fish may be observed underwater. By now, you should know that when we look at objects that are underwater, they always appear to be higher than where they actually are. For example, if we're looking at a swimming pool, we might find, oh, it looks so shallow. And then when you jump in, no, it's so much deeper than it actually is. And the reason for that? Refraction. So in this situation, say we are looking at a fish that's underwater. Now, the fish will be the object, and where we perceive it to be, the fish that we're seeing, that would be the image. So the actual position is where the actual fish is, or the object, and the perceived position is where the image is observed. That means where it's perceived to be. The refractive index can also be calculated based on the locations of the actual position compared to the perceived position. The terms for these are real depth and apparent depth. Now, the real depth is measured from the surface of the water to the actual position of the object, whereas the apparent depth is measured from the surface of the water to the perceived position of the image. The refractive index is a ratio of these two depths. You can calculate refractive index, N, as real depth divided by apparent depth. Now, in all of these calculations, you will find that the refractive index values will be the same when calculating for the same medium. For example, if we were to calculate the refractive index of water, regardless of the formula that you use, you will get the value of the refractive index of water as 1.33. So that's something you should be aware of if you are required to solve problems involving refractive index. Another thing that you should know is that the value of the refractive index of the medium will always be more than 1. And that's because the refractive index of the medium that we calculate is always compared to air. And because we will find that the optical density of the medium will always be higher compared to air, well, whatever objects that we're looking at. For example, if we're looking at materials like glass, water, oil, plastic, all of them will have optical densities that are greater than air. So you always get the value of refractive index that's greater than air. If you calculate the refractive index to be equal to 1, that means that the refractive index of the medium is equal to the refractive index of air. If you calculate the refractive index to be less than 1, that means that the refractive index of that medium is lower compared to that of air. So that's why we always get the value of n to be more than 1. The refractive index of the medium will always be greater compared to the refractive index of air. So that means the speed of light in that medium will be slower than in air. So if it's equal to 1, means the speed of light in air and the medium are equal. If the value of n is less than 1, that means the speed of light in that medium is faster compared to air. You won't come across those kind of situations where n is less than 1. That's not the kind of questions you'll come across. So that's why the simplest way to just make sure that you've got it correct in all your calculations with regards to your questions, the value of n will always be greater than 1. So I hope you found this video to be educational and helpful. Don't forget to click like and subscribe for more physics lessons from your physics teacher, Miss Ho. Happy studying!